Hello everyone. In this video we will continue to examine topic 12.1, the interaction of matter with radiation, and in particular continue to discuss the wave function and quantum mechanics. Alright, so we introduced the idea that quantum mechanics was founded on postulates. And the first sort of big old postulate that we discussed was that the state of a system was completely specified by the wave function psi, such that the square of the amplitude of psi gives the probability of finding a particle at position x. One minor note here. The wave function itself can have imaginary values, and so psi squared is really psi times the complex conjugate, psi star psi. If you've taken HL Math, that comment is just for you. But in any case, let us consider this particular wave function. So this is the wave function of a free or unbound particle, and it's a shape we've seen before. This shape is known as a wave packet. Okay, it looks kind of wavy, all right, but it clearly has a general sort of location, and if it moves along, that wave packet can move, and the location moves. And this is a graph of the amplitude of the wave function. So this is psi right here for a particular free particle. The first thing I'm going to note is that we finally have an answer to the question of what is the de Broglie wavelength the wavelength of? Because the answer is this thing, the wave function. We'll talk more about why it's called a wave function moving forward, but the wavelength itself of that wave packet is related to the momentum and can be measured from the wave function. Okay, so this is what the wavelength is of. It's of the wave function. And moving forward here, you can imagine taking psi and squaring it. So I've ignored the imaginary part here, so this isn't quite right. So bear with me if you have seen this material before. But the general idea is that if I take this function and square it, all right, I will get bumps that correspond to each of the peaks in the original function. Sorry, it should be higher. And it'll look something like this. Okay, so psi squared is all positive, as it must be. And the idea behind the probability is that if I take the area under this curve, okay, the area under this curve from any location, A to B, then I will find the probability of being found, I will find the probability of the electron being found in that region if I go to measure it. So what does that mean? Well, the probability of being found between A and B is just the area under this curve. And for example, the probability of being found sort of in this whole region, okay, under the curve, would be exactly 50%. Okay, exactly 50%. Notice that the probability of being found exactly at A is 0, because psi squared is 0 exactly at A, as shown right here. And the most likely place for us to find this electron is here, right at the peak. Okay, so that would be the most likely place for us to find it given psi squared. And psi squared, so this, the wave function squared, is sort of the essential property that this wave function has. So in some ways it's sort of backwards defined, although we'll see why in a bit. But the fundamental property that the integral of the wave function squared gives you the probability is that first postulate. Okay, it's telling you something about psi. Notice that the entire area under this curve here would be 100%, okay, or 1. Note that the probability of being found here or here would be the same. And note that it's just not true that every time we're going to find it in the same spot. So if we set up this free particle multiple times and we measure the location of the particle very precisely, we could find it here, or we could find it here, or here, or here. But this function, psi squared, gives the probability as a function of position of finding it there. And all of this is true at any particular time, but you might ask sort of what is happening to the wave function over time, and that's where we get the answer to why it is called the wave function. Because it turns out the wave function evolves, changes in time, exactly like a wave in a medium. It obeys an equation that looks like this. This is the Schrödinger wave equation. And fundamentally, although you don't need to know this equation, the psi itself is going to evolve in time in accordance with this equation. And this equation is of the same form as other waves, equations that look at things like water waves or electromagnetic waves. It's of the same sort of type. And as a result, if you actually watch the wave function evolve over time, it looks kind of like a wave in a medium. Very similar. And if this is a free or unbound particle, you can imagine this wave packet moving, literally moving from this lighter position forward. It will also, as it turns out, spread out, although the details of that are bound up in the Schrödinger wave equation to begin with. So, why is the wave function called the wave function? It is a function that obeys this property, and it also obeys the wave equation. And it looks like a wave. If you watch psi evolve in time, it looks like a wave in a medium. There is no great answer to the question, like, what is the medium? Because psi just has whatever value it has. It's a function, okay? It's a function, not anything else. But it has reality in that if you square it, it directly and correctly describes the probability of finding the particle there. And as it turns out, that's the only information that exists. Okay? And so psi turns out to be more fundamental than anything else. So by the end of quantum mechanics, we're very tempted to say the electron just is the wave packet that is its own wave function that evolves in time. There is no extra particle. This just is what exists. And it evolves according to the wave equation and has this particular property.